Remember what my studio looked like in the last video? Well, this is what it looks like now. Hey, I'm Mark and welcome back to my workshop. In my last video, you might have noticed that the backdrop of my studio looked a little bit drab and unfinished. What you are looking at is a fully 3D printed wall backdrop. As you probably guessed from the title, it's also an acoustic panel and it's been fully generated by AI. And as far as I know, an acoustic panel being generated by AI is a world first, which is pretty cool. I dived headfirst into a rabbit hole researching acoustic panel, and there's nothing a maker likes more than a rabbit hole. I discovered these things weren't just any kind of acoustic panel. They're called skyline panels or skyline diffusers. In my research, I stumbled across a BBC white paper written in the 90s that is considered the Bible for creating these acoustic panels. Instead of my usual route, bashing my head against Fusion 360's timeline, I decided to open a new chat with ChatGPT and see what we could. Before we go any further with that journey, let's start with the basic understanding of what a QRD panel is. QRD stands for Quadratic Residue Diffuser, a technical term for what is essentially a very sophisticated sound scatterer. As a thought experiment, let's imagine you're at a calm pond. You pick up a pebble and you decide to throw that pebble into the pond. It creates ripples that spread out in a circular pattern from the point of impact. If that pond were a room and the ripples were sound waves, a flat wall would behave just like a single point of impact. Sound waves hit it and bounce back in a predictable pattern. Now picture, instead of throwing one pebble in, we're going to throw multiple pebbles into the pond simultaneously. The ripples from each pebble interact with each other, creating a complex pattern of wave interactions. In our room analogy, this is exactly what happens with a QRD panel. When sound waves hit the panel, they don't just bounce back, instead they scatter in multiple directions. That scattering effect is key to how QRD panels improve room acoustics. They prevent sound waves from simply bouncing back and forth between flat surfaces, which can create echoes or muddy the sound. Now we know what a QRD panel is, it's probably time to talk about the AI. What I use for AI is ChatGPT, which is probably the most common AI at the moment. I literally asked GPT, do you know what a QRD panel or a skyline diffuser is? Fortunately it did, otherwise this would be a really short video. GPT knowing what a QRD panel is meant that we embarked on a mission to build an OpenSCAD script for a 3D printable QRD panel. Initially, ChatGPT's code had some, let's call them creative moments. It was a bit of a struggle with me often correcting the AI model and it needing a bit of coaxing, but persistence pays off. We changed the approach, and after a bit of a course correction, GPT and I started to actually get somewhere. We were able to actually generate a panel programmatically, but let's not forget the practicalities. This needs to be printed, so the first question here is, will it actually print? It was going to take 18 hours and 250 grams of filament to print a single panel. No dice. Back to the drawing board again. I reached out to my frequent collaborator from the community, Chris Russell, and Chris gave me a great idea, which was, why not try using a different infill like lighting? This discussion with Chris gave me a better idea entirely. These are wall panels. Do I even need a base on them? Do I need infill? I went down to about 130 grams of filament and now a 13-hour print. A few more tweaks later, this is what I ended up with. Armed with my trusty Prusa Mark III's and my Bamboo P1S, I set about printing these panels. Let's go take a look at that. How awesome was that? It's so incredibly satisfying to see an abstract idea turned into a real-world solution. In total, it took about 15 rolls of filament to print about 80 panels, and that was roughly 750 hours of printing across 2 different printers. For the filament, I chose Filamentum Vertigo Grey. This project was not sponsored. I paid for every roll out of my own pocket. Filamentum, if you're watching, send me some rolls. I've got plenty of projects to showcase in the future. If you haven't had a good look at them, let's talk about the actual panels. This particular panel is an 8x9 well QRD with a depth of 5 through 30 millimeters. The base includes 2 mounting options. One is adhesive, but it's also been designed so that you can use a small drywall or similar screw and just slot the panel into position. One of the best things about having my own AI generated panels is that I can do any size. For instance, here is a 13 by 13, 5 through 50 millimeter panel printed by Chris Russell. Now the obvious question is, how well do these perform from an acoustic perspective? We can do a comparison between this video and my last video. There are 2 versions, and the one you're seeing here is my motorized version. However, I do have a hand-powered one that you can buy online on my website. Does it sound any different? Yeah, I think so. But I did ask ChatGPT to simulate the performance of the panels, and it's quite decent. The graph you can see on your screen has several different frequency ranges on the horizontal axis and the simulated performance on the vertical axis. The other thing that influences how well these panels perform is the depth of the wells. Different frequencies require different depths of wells. Unfortunately, for a panel that would work for the entire sound frequency that humans can perceive, we would need a Z-axis of about 700 millimeters. That's just not feasible unless you've got one of those Orange Storm Giga printers made by Allegro. Orange Storm Giga kind of sounds like a new energy drink made by an influencer. Anyway, a panel 700 millimeters tall is just not feasible for a 3D printer. I had to make a conscious design choice on the well depth to keep it practical on a 3D printer. Fortunately, the well depths tend to have diminishing returns and they are well within the realm of possibility for practical 3D printing. 30 millimeters is decent, 50 millimeters is great. The 5 through 50 millimeters has an improved frequency response, but both should actually perform quite decently in the frequency ranges that human voices tend to fall into. Let's move on to challenges and learning, and the first one is obviously working with AI. GPT didn't actually know how to generate OpenSCAD code, so I had to train it in what's called a few-shot model, which means I correct it each time it makes a mistake until it gets better at producing correct code. I also, however, encountered a lot of hallucinations in this experience. AI hallucinations refer to a phenomenon where AI systems, particularly those involved in generating text or images, produce outputs that are unrealistic, nonsensical, or completely unconnected to the intended input or task. Basically, bullshit. What does a hallucination look like here? It looks like GPT trying to use a RAND function in its OpenSCAD code. At first glance, that might seem correct. But you know what? OpenSCAD doesn't natively have a RAND function, and GPT didn't know that, so it tried to use it anyway. A hallucination. Another hallucination might look like AI trying to generate a countersink. It thinks it understands what a countersink is, but let me tell you, if the cone of the countersink is upside down and outside of the boundaries of the physical model, it's pretty clear that the AI doesn't understand what a countersink actually is, but it doesn't know that. It took me a lot of work to manipulate ChatGPT and actually reliably producing OpenSCAD code. AI also has a pretty terrible memory for a machine. It would often forget some of the basic questions that I asked in my earlier queries. I'd set a limitation or a constraint, and then a few replies later, it would conveniently forget about them. Probably the biggest learning for me is that it's incredibly difficult to articulate 3D concepts to a machine that does not necessarily think in terms of 3D. It's awfully easy to think that behind the scenes, this AI model is imagining a 3D model, but in reality, it's just trying to best predict a series of words that it thinks I want to hear, which just happen to be OpenSCAD code in this case. Also, it might sound trivial, but trying to explain 3D concepts to anyone is freaking difficult. It's actually quite similar to the Lego challenge. That's a team building exercise where the goal is for your team to build a model as close to a diagram as possible. However, only one person gets to see the instructions, and that person is not allowed to be the person that touches the Lego bricks or be part of the building process. If you've ever tried it, you know how frustrating it can be, and that was very much how this experience was. Printing also raised its own challenges. The first couple of iterations used a terrible amount of filament, but as mentioned, we were able to revise this significantly. The removal of the base entirely, which led to zero infill, did a lot here. And lastly, only after I printed most of my panels did I send a digital file over to Chris for a test print. And I noticed the bridging on his print wasn't great. This caused me to look closer at my own prints, and sure enough, there was some questionable bridging on my own prints. And that led me to revise my code yet again with the inclusion of a small chamfer on the inside of the model. That really improved the bridging by creating more area for the bridge to be anchored. When I first posted about my wall panels to Twitter, there were 4 overwhelming themes in the responses. 1, oh my god, that's going to create dust. Yeah, it's a fair call, it's a dusty workshop. Don't you guys have vacuums? 2, this is flimsy and it won't absorb any sound. You're absolutely 100% correct. It's not going to absorb anything. It's about diffusing or reflecting it, and at no point have we made any claim about absorption. Also, these things are just not that flimsy. 3, it needs to be made of foam or wood, and again, that's just not true. The original BBC white paper talks about different ways to manufacture these panels, and vacuum forming was one of the ways they thought about. And if vacuum form plastic works just fine, then even more rigid 3D printed plastic is going to be just fine. Since I did this project, there are now multiple projects out there that do similar functions. There is the one I mentioned earlier, and that was by 3D. That said, this is the project that inspired me, so thank you to 3D Printing Academy. There is also another similar design out there by Triple G Workshop. It's designed as a photographic backdrop. It looks pretty much the same, but I can't talk about if it even has acoustic properties. That one is free on printables.com. This project has been an absolute blast, probably one of the most interesting creations I've ever made. It was quite the endeavor, but every moment that I've spent on it has been really rewarding. And it's a unique talking point for my workshop that I can use now as a cool YouTube background that will also help the acoustics of the space. These QRD panel designs are available for digital download on my website. The package includes 60 unique panels in various sizes and depths, ensuring there's something for everyone. Whether you have a small printer or a large one, you'll find panels that fit your needs. A huge shout out to everyone who's already purchased a panel. To those of you who print and install these panels, please don't forget to tag me on social media. I'm really eager to see how you bring my designs to life in your own spaces. Thank you for watching and being part of this amazing project. If you enjoyed this video, please give it a like. Got any ideas or challenges for me? I'm all ears. Drop me your thoughts in the comments. Tell me what you think of these QRD panels. Give me an idea for next time. Your input is what fuels my creativity. Thank you for watching. Stay curious and happy making.